Okay, what we're going to do is start using this moment generating function stuff. I'm just at the Wikipedia page here. Yeah, and it gives you some examples here. You remember I've given you a formula for it. It's just this expectation of eta, it's just that. So there's a whole bunch of different random variables and or distributions at least, and their moment generating function. Now I'm on thin ice here because I normally work with a characteristic function. I think that's a psi of t here, which I much prefer theoretically. I think it's a much better way of doing it. So I work on the right hand column, but I guess the characteristic function isn't part of the course that we're looking at the moment, so we'll just concentrate on the moment generating function, and I'll make sarcastic comments about it from time to time, such as looking at the very bottom entry, which is the Cauchy distribution, and of course the moment generating function doesn't exist for that, but it does have a characteristic function, because every PDF has a characteristic function. Just thought I'd mention that. Yeah, okay, well I'll tell you what I'll do. What I'm going to do is I'm going to use the moment generating function of the binomial to do some stuff with it, and it's this one, 1 minus p plus p e to the t to the power n. Just remind myself what the binomial distribution is. In fact, I'll do it now. Bring this up here. So binomial distribution. You've got n trials where n is fixed, and we've got n trials, each one is a fail or a succeed, Bernoulli trial, and where the probability of a success equals p for probability, and we are going to count the successes. And this is quite elementary stuff here. We've done this dozens of times before. I think I can click this. Yeah, that's better. And the probability, and we're going to call the number of successes r. Probability that the number of successes equals r is equal to n choose r, p to the power r, 1 minus p, n minus r, where p is a parameter and n is fixed. That's the size, not normally thought of as a parameter. Okay, so there's our probability density function. So the moment generating function for this, m of t, I guess, is equal to, well, just copy it off here. I'll derive it soon. It's not as hard to derive. Hang on a minute. Move that down there. It's this one here. This one. You see that one there? I'm going to write that down. 1 minus p plus p e to the t to the power n. 1 minus p, looks a bit of a mouthful, plus p e to the t all to the power n. Now I'll show you how to get that in the next screencast, but for the moment, I'll maximize that. For the moment, I'm just going to use it. So what I'm going to do is I'm going to take a Bernoulli random variable, x is distributed as binomial, bin of n comma p. And what I'm going to do is I want to work out the expectation of, well, let's just try the expectation of x. Well, that's equal to d by dt of m of t, evaluated at t equals 0. From those formulas, I forget which one it was it the third or the fourth? I can't remember now. Alright, so it's d by dt. So what you do is you pretend you don't know that, you ignore that for the moment, of the moment generating function, which I've forgotten. Oh, there it is. 1 minus, up here, 1 minus p plus p to the t. 1 minus p plus p e to the, not it, just p e to the t, just getting that wrong there, all to the power n. So we'll differentiate that, we'll do all the differentiation and then set it to t equals 0. Okay, so what's that equal to? Well, that's equal to p e to the t, 1 minus p plus p e to the t to the power n minus 1. That's just straight chain rule. And then we set t equals 0. Sweet. So of course e to the 0 equals 1. Well, that makes things a bit simpler. So we've got p. I've not done it right, have I? Because I've got, when you differentiate, you take the n down, don't you? That's it. So look, np, e to the t, well, I'll put it in e to the 0, 1 minus p plus p e to the 0 to the power n minus 1. Okay, and that e to the 0 is just equal to 1, so I'll forget that. np 1 minus p plus p e to the 0 is just times 1 to the power n minus 1, which is np times 1 to the power n minus 1, which is just n times p. Well, we knew that. We knew that, didn't we? What I've done is work out the expectation of a binomial random variable, and I've got np. Well, we knew that. Yeah. Well, there you go. At least it checks out. Right, I'm going to stop there. And I'll do something a bit more interesting in the next screencast. Click done.